Okay, welcome back to Natural Language Processing, Part 2, if you will. So we last left off staring at the count and the TF-IDF vectorizers, and since then I've wrote some math on the board. Not tricky math, just mostly words, but still fractions are considered math on Earth, so it's math. As I mentioned before, count is one way of determining how important a word is. You know, data occurred 99 times in the data science article. Does that make it important in that document? Absolutely. Data is a very important word in the data science Wikipedia article. But across several articles, how common is the word data? So that's where the idea of TF-IDF comes in. TF-IDF, again, stands for term frequency inverse document frequency. And it's split up into two things, term frequency and inverse document frequency. So again, consider we have several documents. Again, a document could be a tweet, a document could be an article submitted for a conference. So a document is a collection of words, and each individual document exists, and it is also the whole corpora, the collection of all of the documents. So within a document, in a single document, there is the term frequency of a word, which is very basically defined as the number of times that term appears in the document divided by how many terms there are, or the len, if you will. So term frequency is pretty much what you'd expect. It is the percentage of the amount of times that term appears in a document. So for example, if you have a document with 100 words, and the word cat appears 3 times, the term frequency of cat is 0.03. How many times it occurs divided by how many terms there are. And how many terms there are is repeated, so 100 repeated words. So that's in one document. Now, cat also will have an inverse document frequency, but that's across all of the documents. So each document will have a term frequency for a word. So let's say there are, in total, their n equals the amount, n equals the number of documents as a whole, and maybe that's 10,000 documents. 10,000 documents. Now, there is an inverse document frequency of the word cat. The inverse document frequency stays the same across all of the documents. It is a single global variable that is, of all of these 10,000 documents, this is the inverse document frequency of cat. And it's defined as the log of the number of documents there are, period, divided by the number of documents that has the word cat in it. So let's say there are 10,000 documents total, and let's say there are 1,000 documents with the word cat in it. So of the 10,000, 1,000 of them have the word cat. So we'll divide those two numbers, 10,000 divided by 1,000, which is 10, and then we take the log of that number. What log? You'll actually find that it's different for some calculations, and the reason they do the log in the first place is to kind of is because they're assuming that there's not a linear relationship between how often we use words in documents. They're assuming it's a logarithmic or exponential, or the inverse of each other, a logarithmic description of how often we use words. So for example, if we, as we use words in documents, they're assuming that, okay, well, it's not a linear, it's just going to be kind of a log, so it's going to cap off at a certain point. It's a basic assumption. You don't necessarily need the log but they add the log in as a form of representing the real world, because not everything is linear, some things are logarithmic. So most calculations will do log base 10. Most will do log base 10. You'll see natural log, which is log base e. Sometimes you'll see log base 2. I'm going to use log base 10. So log base 10, so this equals 10, and log base 10 of 10 is 1. Make sure my math is right. Cool. What does that 1 mean? 1, don't think of it as a scale. This is not on a scale of -1 to 1. It's not on a scale of 0 to 1. In fact, this is an unlimited scale, theoretically. You can go up to infinity, theoretically. What it's trying to tell you is how common this word is across all documents. So let's say, for sake of example, out of the 10,000 documents, all 10,000 have the word cat. If every single document had the word cat, that means our n is still 10,000. Now the number of articles with cat is also 10,000. So if we divide these numbers, what do we get? 1. What is log base 10 of 1? Math. 0. There is one limit. As the number of documents that it contains the word increases, the log of that number approaches 0. And if every single document has that word, it's given an IDF of 0. Think of an IDF as 0 as literally being it's the most common word. It's in every document. So as the commonness of the word goes up, as in the more documents it's in, its IDF score goes down. And the higher the IDF score, the more unique a word is. The lower the IDF score, the more common it is. So an IDF score of 0 literally means it's in every document. So it's not weird that you saw it in a document, because it's in all of them. If it has an IDF score of 0.01, it's still not in every document, but it's in most documents. So as the IDF score goes up, it's a signal that your word is rare. It's not in. For example, if it's only in, so here's n is 1,000, 10,000. If it's only in one document, what is its IDF score?
Log base 10.
Log
10,000.
Of 10,000, which is what?
I'm not calculating.
3. 10 to the third power is 3. It's 10,000. Right? Look at my.
Yes.
Okay, cool. Someone. So, the scale depends on the base you use, how many documents there are. In this case, our scale is 0 to 3. That will change if, for example, there are now 100,000 documents. If there are 100,000 documents and it's only in one, now its TF-IDF is 4. So the scale changes based on what base you use as your logarithm and how many documents there are. However, 0 is always the lower bound. 0 is always the case when it's in, no matter how many documents you have, it's in all of them. So all you need to know is 0 IDF is in every document, and the more you go up, the less common it becomes. The more unique, the more rare that word is. So now we have two pieces of the puzzle. A word's term frequency is how often it appears in one document. So for every document,
there is a TF. For every unique document, there is a TF. That TF could be 0. That word could not appear in that document, making the term frequency 0. And the term frequency tells us how important that word is to that document. So if data appears 30% of the time in data science, that word is important to that phrase or to that article about data science, which makes sense. Now the inverse document frequency of the word data is a constant, quote unquote. Quote unquote, because you still have to calculate what it is, but it stays constant across all of the documents. In documents 1, 10, 10,000, and a million, the IDF is the same number. The IDF of cat is the same across all of the documents. So what is TF IDF? TF, term frequency, inverse document frequency, is the term frequency of the word times the inverse document frequency of that word. That's it. So for every document, you have a TF IDF. For every document, each word has a TF IDF, which is calculated with the term frequency of that specific document and the inverse document frequency across all the documents. So how important is this word to this document versus how rare is that word? So, pop hypothetical question. If a word has a very high TF in a document and a very low IDF, what does that mean? Explain to me in words what it means when a word has a high TF and a low IDF. Yeah?
It's very important to what you're reading, but it's not necessarily unique, so it's probably structural.
Well, a low IDF. Yes, I'm sorry. Yes, sorry. Yes. Yes. If something is a high TF, spot on, it means it's very important to whatever I'm reading. To whatever document I'm reading, this is an important word. But if it has a low IDF, it means it's a common word across all the things I could have read. So if I go to a data science conference and I'm reading every single paper out of the data science conference, and I see data is a 60% term frequency in this document. Yeah, it's really important. But data probably literally has an IDF of 0, which means it's probably in every single paper you're going to read. Now, I'll flip it. What if the TF is low and the IDF is high? Term frequency is low, IDF, inverse document frequency is high. It's an interesting use case. What does that mean? Someone on this side. If term frequency is low and inverse document frequency is high, we'll break it down. What does term frequency being low mean? That's so IDF will tell you how uncommon. Well, comment in what case? In what sense? In a given document, if the TF is low, it's not common in this particular document. So maybe the word I'm looking at is monkey. Monkey doesn't appear, it appears once in this whole document. It's not very important. But what if its TF IDF is very high? Or I'm sorry, its IDF is very high. What does that mean? This number, the IDF is very high. What does that mean? It's less common across everything. So it may not be super important to this specific article, but it also hardly appears anywhere. So that also says something. So even though monkey might appear 1% of all the words, its IDF might be extremely high, which means if this is the only article it even appears in, potentially. So it might not be super, super important to this one article, but it's also the only article it appears in. So that also says something. That's why there's two pieces to the puzzle. Because words are now not, because here's the problem with the word monkey. Monkey will always lose out to other more popular words. I mean, excluding stop words, you have very common words like tree. Tree was probably used even more than monkey in that article about the forest. data science in a forest. Tree was probably used more often than monkey. But tree might have been used somewhere else talking about a decision tree or some kind of tree-solving algorithm. So tree would beat monkey in that one document, but it would still be more common than the word monkey across everything. So now we're giving words two things to fight with. How common it is in one document and how rare it is across all of the documents. That's what TF-IDF does. So here on the screen, this is the TF-IDF matrix for those sentences. Bob likes sports, Bob hates sports, Bob likes trees. Down here are the IDFs of each word. Bob has an IDF of 1. The highest IDF is trees. And sports and likes are in the middle. Bob has an IDF of 1, which is the lowest score. So no, it's the lowest score. It's 1, 1.69, 1.28. Bob has the lowest score because why? Why does Bob have the lowest IDF score? It's the only word in every sentence. Bob is the only word that's in every sentence. Therefore, it has the lowest IDF. Why isn't it 0? Because Python is using a different base than 10. It's using something close to 2.
That's going to be my question.
Yeah.
How do you determine what your base is or what base you're using?
It decides. You don't get to change the base, unfortunately. In the standard TF-IDF vectorizer, you can't change it. But if you make your own TF-IDF vectorizer, and by the way, it's not part of the lab, but making your own TF-IDF vectorizer is fairly straightforward. All you need is how many documents there are, the len of your documents, and then for each document, you just check, is this string in it? If it is, add to a counter, and then you have lowercase n. Then you just start dividing numbers, and you have your TF-IDF. So it's actually a very straightforward process to choose your own base. Here, you can't choose the scikit-learn's base, unfortunately. So, yeah.
Are there advantages to using different bases, or
The advantages come with how many documents you have. So as you increase the number of documents, like in the millions, it's usually better to use a higher base to kind of scale it so it's in nicer numbers. But that's usually the only reason. So notice again, we have 3 rows and 5 columns. 3 rows because we have 3 sentences. 5 columns because we have 5 unique terms. Bob likes, hates, sports, trees. Now, the zeros mean that either term frequency was 0, IDF was 0, or both. Now, in this case, we know all the IDFs are not 0. So when you see a 0 term, it's because the term frequency, because it's term frequency times inverse document frequency, the term frequency was 0. Notice Bob is the first column. Now, across all of the sentences, Bob consistently, the first column consistently has the lowest non-zero TF-IDF. Which means as you're reading a document, i.e. a sentence in this case, as you're reading a document, Bob having a TF-IDF of 0.48, whereas the other words have a higher TF-IDF mean, Bob is not an important word, usually. Bob is not an important word in this document. Because it doesn't occur that much, and also it's a very common word. So it's not a unique word to me. TF-IDF is trying to pull out the most unique words in a document. What makes this document unique? Can someone tell me why this might be very, very important? Why would it be very, very interesting and important to be able to quantify unique and interesting words? Well, one guy got bought out for $100 million for doing it by, I think, Yahoo or Google. Document summarization. If I can give you a document and you can summarize that document to me in a few words, that's really big. Because who would use that? News sources. A conference, news sources, any news article in general, like any government document, like give you a long government document, pick out the interesting, important words very quickly, that's worth a lot of money. And that's what TF-IDF does. It picks out the really interesting words. Words that either appear often in single documents or are just very rare across all documents. So, as an exercise. So, I give you the TF-IDF matrix, and you have the IDFs of each word. Here's an exercise. It'll take some thought where you don't have, I didn't give you can't copy and paste for this one. For each sentence, Bob likes sports, Bob hates sports, for each of them, sort the interesting words, i.e. sort the words by TF-IDF in ascending order. So all I want is for each sentence, show me the words in order of least important to most important. By important in terms of TF-IDF. You have all of the numbers up here. So line 291, I give you the IDFs of each word. And this matrix on line 286, each row represents a sentence. Your output, again, the answers are down here. What? You have the TF-IDF. It's in this matrix. So, as an example, for each sentence, Bob likes sports. The two most interesting words are likes and sports. For Bob hates sports, it's sports and hates. And for Bob likes trees, it's trees and likes. So I'm showing you the top two interesting words for each of the sentences. So take 5 minutes and see if you can come up with this output. For each sentence, show me the top two most unique words in that sentence. Because after this, I'm going to apply it to the entire Wikipedia article on data science. So what are the interesting words there? So when you hear for each sentence, your first thought could be, let me do a for loop over each sentence in sample. So for each sentence in sample of index 0, 1, and 2, well, the first sentence is index 0. Row 0 happens to be the TF-IDFs of that sentence. For the second sentence of index 1, row 1, the second row, is the TF-IDFs of that sentence. The third sentence of index 2, well, row 2, the third row, is the TF-IDFs of that sentence. So if we can go through each sentence, we know the index of row. We know which row we want. And how do I get names and TF-IDFs together? This line, 291, will do that for you.
Not the.
So here's my solution. For each sentence in sample, and I'm using syntax that is brand new to this class, but you might have encountered before. Enumerate. Enumerate is a very handy function in Python. If you call enumerate, which is a base Python function, you don't need to import anything. And you'll know because it highlights in purple in Spider. If you enumerate sample, not only will it give you each sentence in sample, it will also give you the index of the loop that you're on. So it goes 0, 1, 2, 3, 4. So it just tags on a variable called index that increments for each for loop. Why? Because for each time I go through a sentence, I want the index that I'm on to call that row in my TF-IDF matrix. So for each sentence, index is going to be 0, then 1, then 2. So I call the 0th row in this matrix up there, or here, then the 1 row, the 2nd row, and then the 2 row, the 3rd row. And I just sort, here I just sort it by the second element, and that's what gives me the 2 most interesting words for each sentence. I am going to keep going because I want to be done with this by 9 so we can start the lab at 9. I think the lab is very interesting. The next exercise I'm just going to do. So it's essentially the same thing, but instead of using those 3 lame sentences, I use the sentences from the Wikipedia article. So for each Wikipedia article, it shows me the interesting words in each sentence. So if we go through these, we'll see, okay, well, prasanada and Indian were the interesting words in this sentence. And the next sentence were stop words, unfortunately. And then statistique and review, which is also the STEM version. Then we have publication was an interesting word in this sentence. Views and workers, largely, and quantitative. So for each sentence, it's showing you, notice that data is data is not ever an interesting word. It's only showing me the words that are rare across the documents, and by documents in this case it's sentences. It's showing me the words that are rare across sentences, but also that appear a lot in this specific sentence. Yes?
Can you, this might be very cool for this, but is there a way to pull out interesting phrases?
Yes, actually. So TF-IDF vectorizer, by default, will vectorize everything tokenize everything into words. And we'll actually see on Wednesday, you can use the TF-IDF vectorizer to not only do words, but phrases. They're called n-grams. An n-gram, so n you spell so 3 gram is a 3-word phrase. So you can tell to pick out not only interesting words, but interesting words, 2-word phrases, and 3-word phrases as well. Does that answer your question? So moving along, I am actually, unfortunately, going to skip this on LDA. I highly encourage you to, I'm going to run it for you, but not, I'm going to run it for you to show you what it's doing, but I don't have time to get into the math behind it, which most of you are saying, yay. LDA stands for latent Dirichlet allocation. Long story short, LDA will take in documents without knowing anything else about it. We'll try to determine topics. It's called topic modeling algorithm. It will take in a bunch of documents and spit back topics defined by important words. So, for example, it will take in 2,000 documents and say there are 10 topics. Each topic is defined with these interesting words. So here's how I'm going to show it as an example. The data set I'm using will actually be from the NLTK corpus, movie reviews. So it's going to actually take movie reviews and try to classify movie reviews into topics based on keywords. And again, earlier I mentioned here we go.
And when you say topics, do you mean like a subset within the document? Because it seems very similar to the other concept, right? Like if you have one document, that would be one topic. But are you saying that if it's one document, you have multiple topics within one document?
So for example, if I give you 10,000 news articles, it would say, okay, I'm going to split these 10,000 news articles into 10 topics. This topic over here uses the words ISIS, terrorist, international, borders. This other topic uses Apple, watch, technology, stock price. This other topic uses sports, NBA, NFL, so on and so forth. So it's splitting up the documents into topics based on keyword. Now, here's a fun little thing I wrote that will pick a random movie review and then summarize it based on unique words and phrases. So, this random movie review can be automatically summarized the following way. One of the first films in 1999 is MTV's picture release, which marks the first leading feature role for James Van Der Beek, the star of WB's Runaway in Dawson's Creek, set in West Canaan, Texas. Van Der Beek does a decent job of carrying his first film, although a silly accent trips him up sometimes. So it's automatically summarizing the entire article by choosing which words are unique and choosing the sentences with those unique words in it. And you do it, you keep hitting summarize, it'll do it for a random article each time. So hitting a random article, it's checking. So here, the flubber is played for gags after it's introduced, but all is forgotten. But afterwards, safe to say that everything can be bad about flubber. Most of the film wanders aimlessly as it relies on the flubber to make for the... So, flubber clearly was an important word. As a word that only appears in this movie review, but not in any other movie review. So it's just picking the sentences with the word flubber because it says, okay, these are the interesting sentences because it has this really unique word flubber in it. Which obviously this is about flubber. So this is what a company got $100 million for doing really well, at least. So you could take in an entire movie review and pick out the key sentences that are interesting and only display those in this, oh dear.
You might want to run a couple.
I'm going to run that again.
I got Big Lebowski.
Run it better.
So no, I got Big Lebowski.
Yeah. But you know it's about Big Lebowski, for
It
example.
starts off with Big Lebowski.
Big Lebowski. So it's like picking out the interesting words. Big Lebowski was the name of a movie, is a very unique phrase in and of itself because it only appears in this one movie review. All right, so that's what LDA does. Using TF-IDF and LDA, it's actually taking out topics by keyword and then showing you the sentences with those keywords in it to try to summarize the document. So we're going to move on to the last part, which is sentiment analysis. This is the part that you're going to need for the lab, so that's why I wanted to hit on it. So the last thing I had you download or install was called TextBlob. TextBlob is a built-in Python module for sentiment analysis. What is sentiment analysis? Sentiment analysis is a way of taking in text and spitting out how positive or how negative something is.
It could also do more text processing. Not only could it tell you how positive or negative something is, it could tell you how subjective a sentence is. How much of an opinion something is. So let's go ahead and just start using it, and we'll actually see how powerful it can be. So to use it, you create a blob object, and you input in a sentence. Liam and Sinan are instructors for General Assembly. That's a sentence. Blob has built-in word tokenizing. So here's the word list. Liam and Sinan are instructors for General Assembly. It can also very quickly point out the noun phrases. Noun phrases are phrases that of themselves are nouns. So Sinan is a noun, Liam was a noun, General Assembly was a noun. So that's a very simplified way of pointing out noun phrases and also verb phrases and things like that. But here's the interesting part. Here's the cool part, I think. Here's a new sentence, or here's a new couple sentences. I hate this movie. This movie is not very good. So I'll make a blob out of it. I can tokenize it into sentences. So each sentence, I hate this horrible movie. This movie is not very good. I can give the overall sentiment polarity, which is a number between -1 and 1 that quantifies how negative or positive it thinks this entire document is. So -0.68 is on average how negative this article is on a scale from -1 to 1. So pretty negative, which makes sense when you say, I hate this horrible movie. This movie is not very good. It could also do a polarity for each sentence. The first sentence was clearly way worse than the second. The first sentence being, I hate this horrible movie, has a -0.9. This movie is not very good, only has a -0.26. So one sentence was clearly worse than the other. So you can find the polarity for each sentence. Subjectivity is really cool, I think, but I would take it with a grain of salt, because subjectiveness is in and of itself subjective. Here's what I mean. I am a cool person. Has a subjectivity of 0.65, which is on a scale from 0 to 1. 0 being very objective, 1 being very subjective. I am a cool person is a pretty subjective thing to say. I am a person is not a subjective thing. Is 0. It is a very non-subjective or a very objective thing. So it tries to do it does its best to try to figure out how much of an opinion a sentence is. So for example, I could also write, instead of I am a person, that thing before, I hate this horrible movie, pretty subjective. Fair enough. I hate this movie is a very subjective phrase. So it might be very negative, but it's also very subjective. So the combination of these two numbers can be very important. Because if someone says a very negative, subjective thing, someone's complaining on the internet. Whoop-de-doo. Now, if that sentiment is very negative and the subjective score is very close to 0, what does that mean? Because what they're saying is bad, but also what? Probably true. Harsh. It's a very objective thing. This movie didn't, the movie theater didn't, play the end of the movie. It's not a subjective thing that happened. And that can be a negative thing that's very objective that has to be dealt with more, other than, I thought this movie was a load of crap. It was very negative, but a subjective statement. That's one person's opinion. So the combination of sentiment and subjectivity can be very important. So here, I have two sentences. Liam and Sinan are instructors for General Assembly in San Francisco with a subjectivity of 0.5, which, again, I'm just showing you the limitations. It's not perfect. Sinan and Liam are instructors for General Assembly in San Francisco is not a subjective statement at all. It's very objective. It's just stating a fact. Patrick and Sinan are instructors in Texas has a subjectivity of 0. So the mere presence of for General Assembly
makes it think that it's a subjective statement. Because if I say for General Assembly, it's like, well, that could be an opinion. I mean, we all know it's not an opinion, but it doesn't know the difference. We can singularize words. Put away the dishes becomes put away the dish. We can pluralize each of those words. Puts, aways, does, dishes. Again, pointing out some of the limitations. So we can pluralize and singularize words. There is automatic spell correction. So you can actually correct the spelling to the best of its, like Microsoft Word ability. It can correct the spelling of a text that you have. So for example, if your project entails user written data, this might be a very simple way of correcting some of the very basic spelling mistakes that people make. Parrot can spell check into either part, which is it thinks a 99% chance of being part, or the word parrot, which is a 0.007% chance. Does anyone want to wager a guess as to why part has a much higher probability than parrot? What do you think it's using? So what is it using? The IDF. So which spelling it's suggesting is completely based on an IDF of what? Of what is called the natural corpus. Stanford, whoever wrote this, probably Stanford, has a word bank. They usually just scrape Wikipedia and just say these are words that are used sometimes in nature. And they're saying part has a much, so if it's more common, has a very low IDF. A low IDF means it's very common, which means it's more likely to be the word that you're trying to spell. What it doesn't do is look at context. So if I wrote, oh, my parrot just flew out the window, it will still probably say part, because it's not looking at the context of the sentence. So take that with a grain of salt as well. It can define words. Bank.define will show you, a depository financial institution. Right? Also, if you scroll down, you'll see trust. Why does trust appear? How can you use bank as a trust word? You bank on something, right? If you bank on something, you're trusting it. So trust is actually a synonym of bank, depending on how you use it. However, if you define it in terms of only as a verb, then it shows you what's called a synset. A synset, and this is getting into kind of more complicated stuff that I'm not going to get into because we're running out of time already. To bank, you can deposit, you can trust someone. Bank has several different meanings. But you can specify the part of speech that you want, and it will show you different definitions as well. The last thing, promise that you can work on your lab. Blob, welcome to the classroom. Translate to Espanol. Whoa, hello. You're supposed to translate that. No. Bless you. Why are you not working? Well, that one was anticlimactic. But it knows Spanish as well. It knows not just English. If I say hola amigos and I say detect language, it will say ES for Espanol. So it can do basic translations. It usually can do basic translations, and I'm very mad that it's not doing a basic translation. Hello? Why are you not? Well, so that's the second blunder of the night. The word tree not working, and now it not knowing Spanish as well as it was supposed to know Spanish. We talked about this. But it can recognize, so what other languages does it know? Does anyone here speak French? Can someone say, how do you say hello in French? Does anyone know? Bonjour. Like that, right? So does it know French? It does know French. What's Russian for hello? Anyone? Привет. Привет? Like that?
Without the G. Without the J.
Oh, is that?
Close enough.
Well,
I mean, it's English.
I don't know what HT is, but it's, how do you actually spell привет? What?
It's relative available.
Yeah, because
Oh, well. How about another word? How about another language? Shall. So it knows some of the basic languages, Italian, French, and Spanish. And if this were smart enough, it would freaking translate. You're just not doing what I want you to do. That's fine. Okay, so this ends my topics in natural language processing. And what I would like you to work on for the next 30 minutes is the lab. The lab is, there's only 6 things to do, quote unquote. One of it is read in the text file, which I've already read in for you. Here's what it looks like. I want you all to import a CSV called so many tweets.csv. What it is every single tweet that I've collected in the month of May 2015 that uses hashtag AAPL, which is Apple's stock ticker. So every tweet, that's a very light color, every tweet that uses hashtag AAPL in the month of May 2015 that I collected is in this tweets. The columns, there's only 4 columns. It is text, which is the literal text of the tweet, the date at which it happened, status, which is a unique status ID on Twitter, and retweet. If it was a retweet, retweet contains the status that it was retweeted from. So, what I ask you to do is the following. Use the text blob module, which we just saw, to find the sentiment of each tweet. And turn that into a column. So like sentiment of that tweet. Use the text blob in the map feature to map text blob to each one. Then make another column called day, which holds the unique day that it was tweeted. So forget what time of day it was tweeted. So if it was May 24th, 2015, that column should be May 24th, 2015. So some unique day column. And then, for each day, show the number of tweets and the average sentiment, so a group by, and then graph them. So, through the month of May, show the change in average sentiment and volume. Volume being how many tweets there were in that day. And then, if you have time, try taking some of the noise out of the tweets, like remove the mentions or the RT for retweet. So remove some of the noise words out of a tweet. So that's the lab, is to work on this data set. By the end, you should have graphs that actually show the rise and fall of sentiment and volume. And then we'll try to match those up with events that actually happened in Apple in May 2015 to see what was talked about and what was negative and positively favored. And so please work by yourselves or with your table or with the person next to you. This is what we're going to be working on for the remaining 30 minutes. Go. Yes. In my Slack, I have to look up the coding. Okay. Try doing these 3 lines of code. You remember this? You get the same thing? So make sure, like, so you're actually getting the actual definition in the later version. You have the one that we're trying to do. Since it actually shows the definition of the word. So it's the same thing.
same thing as we lost.
Yeah.
Yeah, and I see the great
Yeah.
I'm in the data.
Yeah.
Here's all.
Oh, you know what? Actually, maybe I need to go see data. That's not there. Oh, okay. Well, so that says in homework, right? So if I click here, it's there now. Now it's firewalls, you can just click forward. You teaching?
So this is also Python. So if you do so it's going here, it's the dirty cat. Also, there's another way of doing it. Just download it right? You can do Honda. Because that's a different.
Okay, cool. Thank you so much.
I don't know what's that. So you know, I don't know. I think remember red. Don't you make solutions? Freda, did you still have a question, or is he? Stop recording because it's not able to use this stuff.